Here we see an overhead view of the complete two-fault tolerant cold gas propulsion system mounted on its air-bearing platform. On the left is the actual hardware setup, with the front facing upward and the back facing downward. On the right is a CAD drawing of the same system which highlights the 4 thruster lines and labels each valve sequentially. Each thruster line consists of 3 valves and 2 plenums. For this demonstration, we're going to attempt a forward translation, which will use thrusters A and D. Thruster A will experience 2 valve failures in the process, and we will observe the resultant motion. This is considered to be the worst-case failure mode, since both failures will be concentrated in the same thruster line. Specifically, we will be failing valves A2 and A3, and therefore we will be commanding valve A1 to open in order to produce thrust from this line. Strictly speaking, however, nominal operation would not include opening any of the first-in-line valves during a thrusting maneuver. If operators are unaware that both plenums in thruster A are empty, then a forward command, which would open valves A3 and D3, would not produce any thrust from line A. On the other hand, if operators are aware that both plenums in thruster A are empty, then either the satellite can be reoriented and a different combination of thrusters used, or valve A1 timing can be adjusted such that it imparts an equal impulse as a nominal plenum discharge. For the time being, however, we will decide that perhaps our operators just didn't get enough sleep, or perhaps an intern pressed the wrong button, and as such, valve A1 will be commanded open for the same amount of time as valve D3. Because of this, we expect the thrust from thruster A to remain constant, while the thrust from thruster D to reduce over the duration of a single plenum discharge. So here we have the air-bearing platform on the table. Placed in the middle of the platform is an Aruco fiducial marker. Our computer vision script will determine the position and orientation of the marker relative to the camera in each frame of the video and return a time series dataset that we can then use for post-processing in a Kalman filter. As described, we will be using these 2 thrusters to produce a net thrust that will propel the platform forward. The yellow arrows indicate the direction of exhaust, and the red arrow indicates the expected direction of motion. During normal operation, these 2 valves would be commanded open to discharge the gas stored in each second stage plenum. However, these 2 valves are currently failed open, and therefore neither plenum in this thruster houses any propellant. Therefore, these 2 valves will be commanded open instead. So, let's see how this goes. Well, that was exciting. So let's look at it quantitatively now. With computer vision and Kalman filtering scripts, we can measure the translation and rotation of the fiducial marker relative to its starting point. This data is then passed through the Kalman filter to estimate the velocity and the acceleration. We can see here the overall combination of thrust produced a sizable coupled translation and rotation. But what's perhaps more interesting is this little bump right here. In all 3 trials, we see a slight positive rotation before quickly diving into the negative. Recall that both plenums in thruster A were empty, while thruster D was operating normally, with that second stage plenum ready to go. When both valves opened, thruster D began to fire immediately, but the gas from thruster A first had to pass through the 2 empty plenums before being discharged. That time-delayed thrust meant that, for a brief moment, the only thruster firing was thruster D, so it produced a torque in the opposite direction before it was quickly overcome by thruster A.